Hi, in this video, we will learn how to solve the parabolic PDE by using the numerical method. In the previous chapter, we have this Laplace equation, which is in elliptic PDE format. We are going to find the solution for the T, which is the temperature, at location X and Y location. The temperature doesn't change with respect to time here, so we can say that this is time invariant steady state problem. This is the heat conduction equation, which is a parabolic PDE, where you can see we are going to find the T, which is the temperature, at the location X at a particular moment T. The delta capital T here divided by delta small letter t is not equal to 0, which means the temperature capital T here is changed with respect to the time. With that, we can say this is a time variable unsteady state or the transient problem. We can use the heat conduction equation to predict the temperature at point X at a particular given time. Imagine that you have a root here where initially the temperature is 30 degrees Celsius. Let's say you start to burn the thing in the end of the corner where it is equal to 100 degrees Celsius at the left hand side. And in this case, you will find that the temperature at this point start to increase first, followed by the next point and the next point. Let the X to be your horizontal axis, and then you have the X1, X2, X3 represent the position at 1, 2, 3 here. Then you have the temperature, okay, for the point 1, temperature point 2, and point 3. If you measure the temperature at point 1, point 2, and point 3 with respect to the time, you will find that at time equal to 0, you obtain the temperature to be 30. As time passes, you can see that at this point is burned by this source. Therefore, the temperature here will be always to be 100 degrees Celsius. Since X1 is closer to the heat source here compared to the X3, therefore you can see that as time passed by 10 seconds, the temperature at point 1 increased by 30 degrees Celsius, while the X3 there is only increased by 10 degrees Celsius. As the time passed to a large extent here, we can see 10 to the 1000 seconds, the temperature reached to the maximum at all the points, which is 100 degrees Celsius. And if you continue hit the bar by longer period, let's say 2000 seconds here, we found that the temperature will remain at 100. So why 100? Why not more than 100? Is because your heat source is equal to 100 here. And this is your boundary condition. As you can see from this table, when the time greater than 1000, the temperature doesn't change with respect to time. So this is called steady state condition. And for the time less than 1000, the time is changed with respect to time. So this is called transient condition. So you will find in the solution that your temperature will change with the time in the beginning. As the time passes for a large extent, then your temperature doesn't change anymore. Therefore, you should see the relationship between the elliptic and parabolic PDE. The solution for the parabolic PDE is transient at the beginning, and then as time goes, the delta t over delta t here will become 0. This changes the parabolic PDE into the elliptic PDE format, where from here you obtain the steady state result. In simple, for the elliptic PDE problem, you can find the solution in the steady state condition. For example, from this 2D problem, you can find the temperature at the dimension X and Y to be steady state. From here, it will be a 1D problem where you can find the temperature with respect to X dimension. So you obtain the result in steady state condition as well. For the parabolic PDE, you can find the solution in the transient condition. When the time passes to a last extent, let's say t approximate to infinity, where your delta t over delta t here is equal to 0, then you will find that the temperature to be constant, and this is the steady state condition. It means that we can find the transient and steady state condition from the parabolic PDE as well.